Got good news for us here. If you enjoyed the previous section and you thought that it was like puzzles, saw what I was saying, how it could be kind of fun and just to enjoy just kind of trying different things, playing around with things, figuring out, well, you get another day of the same thing, another section of the same thing, some more puzzles, more fun puzzles to play with. On the flip side, if you didn't feel that way, if you thought some of those were a little bit tricky, a little bit tough, wanted more examples, needed a little bit more practice to try to get the hang of it, well, ask and you shall receive. That's what we've got for you right here. Another day of practicing basically the same thing. And more good news, you're basically doing the same thing as the previous section, but I'm going to tell you the answer. Before, you just had to simplify. You had no idea what the answer was supposed to be. You just had to keep working until you got to something that seemed simpler. This one, I'm going to tell you what it should look like when you're done. You just have to show me the work. You have to show me how you get there. How do you get from one side of the road to the other? But you'll already know where you're supposed to be going, what the answer should be. Okay, so we're verifying, or in other words, proving. I try to say verify instead of prove, though, because sometimes people have flashbacks to honors geometry, the two-column proofs. Some people didn't like those so much. We're not doing anything like two-column proofs, nothing like that. You don't have to say your reason for every step. You don't have to justify why A equals A or something silly like that. You just have to just show the steps. So just do everything that we did yesterday. So we're going to pick one side, and we're going to do exactly what we did yesterday, rewrite it, simplify it, play around with it, do different things till something happens, until we get to the other side. So we can't work with this as an equation right now. You can't say, like, you couldn't divide both sides by cosine right now. That would not be allowed, because the whole thing, if we're verifying, if we're proving, it's like there's kind of like an implied question mark right here. Like, does this actually equal that? That's what you're trying to show. Is this equals actually true? So if you start by treating it like an equation, where you divide both sides by cosine, well, if it was an equation, we wouldn't have anything to prove. We're trying to show that this is an equation. So we can't assume that this equals is true. We can't assume that it's an equation, that it's an equals there. So as it says, we have to just pick one side and just work with that side. Right? And so we try to pick the side that's a little bit more complicated. It seems like there's more things that we can do, more stuff that could happen. And so, of course, on this one, we'd pick the left side, because the right side is already pretty simple. Right? Kind of look like this looks like the problem, that looks like the answer. So pick the side that looks like the problem. Right? And so we're going to kind of ignore that for a little while. We're going to pretend like the problem is just simplify that. But the one advantage we have is we know that the answer should be sine of theta. If we do this problem correctly, our answer should be sine of theta. Okay. Well, remember, one of our guidelines was changing things to sines and cosines. So we're going to change this tangent to sine over cosine. And then that's times cosine theta, which is, of course, cosine theta over 1. So then those cosines can cancel out. And so we do get sine of theta. Okay, so we picked the left side and we simplified it down, and we got over to the right side. So you can make your own joke about, why did the mathematician cross the road, or something like that. Why did the mathematician cross the equation? How do we get from one side to the other? That was our goal. All right, and we accomplished our goal. And so what you'll often see in these kind of proofs is that people will put some sort of symbol at the end, either an open box or a filled in box as kind of like a period at the end of a proof, or maybe even exclamation point, depending on how excited you are about your proof. Sometimes you'll often see QED as well at the end of proofs. It's for a Latin phrase. It means something like "I have demonstrated it." Abbreviation of a Latin phrase. I had a student one year who created their own thing to put at the end of proofs. They put YID. They created their own abbreviation, or I guess it would be acronym, of how they wanted to be excited when they were done with proofs. YID stood for "Yay, I'm done." Yay, I'm done. So that was just their their own little thing they created. You don't have to do anything like this, of course, but you know, when you get to higher level mathematics, you do see a lot of proofs of these kind of things where you do some work to verify that a statement is true, and so usually there's something that shows that, hey, this proof is complete. I have demonstrated it. It's done. But you don't have to. So let's take a look at the second one here. On this one, we wouldn't work with the left side. We would work with the right side. So again, the right side kind of looks like the problem. The left side kind of looks like the answer. There's more to work with. There's more to do on the right side. So we're going to pick the right side and simplify. There's a few different ways that we could do this. So pretend like that's the whole problem. Just we know that that should be the answer. A few different ways you could do it. So one way is you could say like, hey, I've got a squared there. Squared means maybe use a Pythagorean. And so you could look to use a Pythagorean on this. Now, if you have all three memorized or you know all three, then that's good. You're good to go. I don't always remember off the top of my head what the other two are. I know sine squared plus cosine squared is 1. And sometimes I kind of forget, you know, what's the other one? Like which one's on the side with a 1? How exactly does it work? Well, again, if you wanted to figure those out, so I want one that has secant in it. Well, secant's 1 over cosine. So that means I need to divide everywhere by cosine squared. That 1 over cosine squared will get me secant squared. So then sine squared over cosine squared is tangent squared. Cosine squared over cosine squared is 1. And then 1 over cosine squared is secant squared. Right? So if I forget those other ones, that's what I usually do. I go back to sine squared plus cosine squared and I figure it out. So then what that means here, secant squared minus 1, we'll take a look here. If I subtract 1 to both sides of this equation right here, what I'll get is that secant squared minus 1 would be tangent squared. So I can say that this right side of the equation here would equal tangent squared x over secant squared x. And then I could change everything to sines and cosines. That would be another way that you could do this in the beginning if you wanted to. You could just make that 1 over cosine squared, make that 1 over cosine squared, deal with that complex fraction. Probably be a little more work, but you could do that. Again, that's one of the fun things about this. They're puzzles. There's lots of different ways to do these. Just kind of play around with it, try something. If what you are trying isn't working, go back to the drawing board, try something else. Just play around with it till it works. So then we've got tangent squared, that's sine squared over cosine squared. And secant squared is 1 over cosine squared. And so then I'm going to make this division. I'm going to change the division to multiplying by the reciprocal. So I'm going to have sine squared over cosine squared. And then instead of divided by 1 over cosine squared, I'm going to make that times cosine squared over 1. Just make sure when you switch it to multiplication that you do actually flip this fraction, right? Do make sure you actually do the reciprocal of that. That's a common thing. People forget to actually flip that fraction. And then, of course, these cosines will cancel out. And look at that. We've got sine squared. We accomplished our goal. We got to the other side. That's the one that I like to choose because I'm lazy / efficient, and that's the one that requires the least pen strokes. Right? So that's one way that we could solve this. Another way would be, wonder if you know that there's a distributive property of division. So usually you learn distributive property of multiplying the bunny ears. There's also distributive property of division. What if we divide through here? What if we say this is secant squared x? And if you were really comfortable with the distributive property of division, you probably wouldn't have had to write this first step here. But distributive property of division, I can say that both of these get divided by the secant squared and rewrite it that way. All right, well, secant squared over secant squared, that's 1. And then 1 over secant, well, that's cosine. Well, 1 minus cosine squared, that's a Pythagorean, right? If we take a look at sine squared plus cosine squared, if I subtract that cosine squared over there, 1 minus cosine squared, I'll be left with sine squared. So there we go, it works out. Another way to do it, and like I said, there'd be another way. You could have made it 1 over cosine squared there, 1 over cosine squared at the beginning. Deal with that. There's probably other ways. There's lots of different ways to do these. That's part of why I think they're fun. They're puzzles. Just try things. If what you're trying isn't working, try something else, including maybe trying the other side. Maybe if you picked the right side and nothing you're trying is working, well, maybe you needed to pick the left side. It's not always as clear of a choice as these have been. Like these, it was very clear which side was the problem and which side was the answer. It's not always as clear. So sometimes maybe pick the wrong side. So if it's not working, try picking a different side. Or just try doing something else. Just to play around with it till something works. All right, so we'll take a look at this one here. This one also is pretty obvious that this side is the problem and this side is the answer. Okay, we're adding fractions, so anytime we want to add fractions, we need common denominators. That's why I kind of left myself some space here in this problem, so I could do these common denominators. So this one needs to be multiplied by the 1 minus sine x. And notice again, I need to actually make common denominators. I can't fraction bust. I can't multiply both sides of the equation by the same thing to cancel out these fractions because I'm trying to prove this is an equation. Remember, that's what we talked about back here. You can't work with this as an equation. We have to just pick one side and work with that one side. So no fraction busting, no fraction busting. Just make common denominators. So this one needs 1 plus sine x, 1 plus sine x. You're always allowed to multiply by 1 in any form, anything equivalent to 1. Okay, and so then this left side here is going to equal 1 plus sine x over 1 plus sine x times 1 minus sine x. And then this right here is 1 minus sine x, and then that same denominator. Right, well, take a look at what's going to happen here when I add these together. So I've got this common denominator. So these are going to be added together. Well, I've got a plus sine x and a minus sine x. So those sine x's are going to cancel. So my numerator, all I'm going to have is 1 plus 1. I'm going to have 2 in my numerator. And then my common denominator, I could just leave it like this, but I'm going to have some more work to do. Let's try to multiply this all out. So you might be comfortable doing that already. If you're comfortable just multiplying it as is, that's great. Again, if you have any trouble, think about this as something like 1 plus u times 1 minus u. So we've got a nice difference of squares pattern here. This is going to be 1 minus sine squared x, because 1 plus u times 1 minus u, that would be 1 minus u squared. All right, well, again, we've got a nice Pythagorean here. I think very similar to one we just did. So 1 minus sine squared. So if we take a look at sine squared plus cosine squared is 1. So if I subtract sine squared to the other side, subtract sine squared from both sides, I get cosine squared equals 1 minus sine squared. And so this equals 2 over cosine squared. Okay, well, we do need it to look like this. We need it to look like 2 secant squared x. But these are identical. You might be comfortable with that right now. You might look at this and say, hey, cosine in the denominator, that's the same thing as secant. And so you might feel comfortable just going right to saying that does equal 2 secant squared x, and that would be okay. If you're not sure why that's true, if you feel like there needs a little more proving or verifying going on in there, the extra step that you could say is you could say that equals 2 times 1 over cosine squared x, and then the 1 over cosine squared is the secant squared. You don't have to, but if you're a little uncomfortable with that, you could put that extra step in there. All right, so we got to the other side. We worked this problem out, and we got it to match the other side, so we're done. We've proven it. We've verified it. Okay, so I've got a couple of these for you to try, a couple puzzles for you. Hopefully you'll have a little bit of fun, at least, maybe, playing around with this. And there's lots of different ways to do these, especially this first one. When I show you the answers, I'm going to have 3 different ways that you could solve this one here. There's probably more, I'm sure, but there's 3 fairly common ways that people solve that first problem there. Lots of different options. So again, just try things, just play around with it, just do different things, make things happen, keep working on it until it matches that other side. Okay. And then same thing with number 5. Number 5, you might have to think a little bit more about which side you want to work with. Number 5, it might not be quite as obvious which side to work with. It's not quite as clear of a, one side's a problem, one side's an answer. So again, if you try one side and it doesn't work, try the other side. All right. So you go ahead and give numbers 4 and 5 a try here. All right. So again, it's not so much showing you the answers here, it's showing you just the steps how to get there. The whole idea is we know what the answer should be. We're just trying to prove that it's true. So I'll show you a few different ways that you could have done these here. So number 4, one way would be to use this Pythagorean here. This was one of our identities. We knew that tangent squared plus 1 equaled secant squared. And again, for me, I didn't necessarily know that off the top of my head. But I know that there is one, and so I can get it from sine squared plus cosine squared. But that is one of our identities. It was on this sheet here from the previous day, tangent squared plus 1 equals secant squared. All right, just remember again that these are only true if we got the squared. It has to have the squared on it for these to be true. All right, and so we can replace tangent squared plus 1. Cosine squared minus 1, we'd have to be careful. That is negative sine squared. So when we rearrange that one here, if you do cosine squared minus 1, well, if you subtract that 1 over, you've got everything on the left side, and so you would have to subtract the sine squared over to the right side. You'd have to subtract the 1 to the left and subtract the sine squared to the right. So cosine squared minus 1 would equal negative sine squared. And then rewrite secant as 1 over cosine, and then that works out pretty nicely. Another option would be you could go right to changing everything to sines and cosines. So you could put tangent as sine over cosine right there. You would still do the Pythagorean for cosine squared minus 1. You could do common denominators inside the parentheses there. Make this 1 be cosine squared over cosine squared, multiplied by cosine squared over cosine squared. And then when you do those common denominators, you get that nice Pythagorean in the numerator there. Sine squared plus cosine squared would be 1. This negative sine squared would just kind of be sitting here all this time. You'd be working inside these parentheses for a little bit, but eventually that would be 1 over cosine squared times that negative sine squared. Will work out nicely again. Another thing that people often try on this is they say, well, let's just multiply this all out. Do FOIL or the double rainbow, or use the box, or however you multiply these things out here. Just multiply that all out, and you would get all these different pairs. And then still we'd have this cosine squared minus 1 becoming negative sine squared. That would still happen. This tangent squared times cosine squared, again, tangent, sine over cosine. We get some nice cancellation there. And you would end up having sine squared minus sine squared canceling out. And so looks like I missed the period at the end of my proof here. So that would equal negative tangent squared x. Let's put that exclamation point at the end there. But again, that works out. So three kind of similar, but also very, very different ways to do the same exact problem. Okay. On number 5, one thing that you did have to realize was that you wanted to work with the left side. Right? If you tried the right side, multiplying things, not a whole lot happens. Adding is better to work with, because adding, we do common denominators. Adding and subtracting, more happens. More happens when you're doing adding and subtracting, because you got to make those common denominators. Multiplying, not so much. There wasn't really much to do from there. So we had to pick the left side. Probably the most straightforward way was to change both of those to sines and cosines. Make your common denominators. Then your numerator was a nice Pythagorean identity right there. And then this 1 over cosine sine here, sometimes it takes people a minute to see that can actually equal what we wanted. That can actually equal the secant times the cosecant, because 1 over cosine sine is the same thing as 1 over cosine times 1 over sine. So that one does work out there and give us the answer that we wanted. Okay. Another way that you could have done it was change the cotangent to 1 over tangent. Cotangent is the same thing as 1 over tangent. And if you wanted to look at any of these more to be able to see kind of the problem and the work at the same time a little bit better, remember there's always a link to these in Canvas. And then when I ask you questions in Pear Deck, in the Ed puzzle in the video, there's always a link to it as well. So you always have a link to be able to look at these filled out notes if you want to be able to see them in the whole page a little bit better. But we changed the cotangent to 1 over tangent, make common denominators, and then tangent squared plus 1 is a Pythagorean identity. And then we change things to sines and cosines, and then it ends up working out pretty nicely. So that way it takes a little bit longer, probably a little more work, but it does get there. In general, I would say, it's often better to change things to sines and cosines than it is to, say, make everything be tangent. Once in a while, it might work better to do something like this, but often it's better to make everything be sines and cosines. All right, so we can kind of zoom out again for just a minute so you can maybe see that a little bit better, or just take a look at that link in the Canvas for those filled out notes. The filled out notes link will show you all this stuff here. Again, I hope you're trying to enjoy this a little bit. See these as puzzles. See this as fun challenges just to play around with. Have some fun with these.